Evening. Can you hear me?
Hello. Yes.
Yes, thank you. Okay, so let us start the lesson today. So we want to talk about infinite series today. So what is the infinite series? So an infinite series, or simply a series, is a formal sum of infinitely many terms. So a1, a2 up to a infinity. So we can simply denote it by this. It means that you have an infinite sequence, and what you are doing, you are adding the terms of this infinite sequence together. But of course, it sometimes happens that this doesn't converge to a definite number. In that case, we say the series diverges, and sometimes this happens that this series uh, converges to a definite number, so then we say the series converges. But of course we need to have a formal mathematical precise definition. So what is the definition? So if you have this sum, you define a new sequence out of this sum, and then, for example, denoted by S, we say S1 is defined to be A1. S2 means the sum of the first and the second term, so definitely you don't have any problems with that. You are adding just two numbers, it becomes a new number. And you calculate S3 by defining it as the sum of the first three terms. And then you get a new number, and then you continue this and you write to Sn, we reach to Sn. Sn means the sum of the n terms, and then you can continue so forth. So if I ask you what are you producing on the left hand side, you would say that I am producing a new sequence out of the terms of my infinite series. And then this is the definition. If this sequence, which is called the sequence of partial sums, converges to a number capital S, we say that our series also converges to the same number. So that is the definition of the sum of a convergent infinite series. And if for any reason this new sequence that you are generating diverges, we say that this infinite series also diverges. If it diverges to infinity, you would say that the series also diverges to infinity. So the whole point is that if a series is given to you, you first generate a new sequence out of your series and then talk about the limit of that sequence that you generate. Okay, so for example, there are many examples that we can bring up, but I told you that I only focus on around the problems which seems to be more important for the people who design the questions for the exam. Okay, for example, determine if the following series is convergent or not. If it is, determine its sum. Okay, so you see that this is a series from number 1 up to infinity, so that's an infinite series. So how should I calculate, how should I determine that if this series is convergent or not? First of all, I need to calculate Sn, means I want to find the sum of only the first n terms, yes? To see if I can say something about Sn. The problem is exactly this. Calculating this sum is not always simple. This is why we actually discuss so much about convergence of series, because in principle, most of the time, this sum cannot be written in a closed form. A closed form means a formula without these dots, which actually is equal to this sum. Sorry. Okay, so how should we do that? What is A1? A1 means this is my AN. I replace N with 1, it gives me A1. I replace N with 2, it gives me A2, and finally I give N to this, it gives me AN, and I want to add them. Okay, so let us see what happens. So I intentionally write it in this form. A1, I replace N with 1. A2, I replace N with 2. A3, I replace N with 3. And finally I continue until I replace N actually with N here. Yes? So this is what exactly I mean. So in principle, calculating this sum is not possible for most of the cases. If it is, then we are not in trouble. We just calculate this sum, it becomes a closed formula, and calculate the limit of that closed formula. If it is a number, we say that this converges to that number. If it is infinity, we would say that this diverges to infinity. Or if for some reason we realize that this is just divergent, we say that this series is divergent. So here, usually if you are able to calculate this, and that is telescopic sum. Sometimes telescopic sum will help you to calculate this. What does it mean? It means that you need to be a little bit creative and experienced in these kind of calculations. So for example, let us consider 1 over k times k plus 1. So you see, it is not a standard problem at all, so it needs experience. Instead of 1 in the numerator, I can write k plus 1 minus k. Okay, I can write a lot of things in the numerator instead of 1, but I decided to write k plus 1 minus k because k and k are gone, and then I am left with 1. But what is the benefit of that? The benefit of that is that I can write it as k plus 1 divided by k times k plus 1 minus k divided by k times k plus 1, and in the first one, k plus 1 and k plus 1 are simplified. In the second one, these are simplified. So I will get this expression, 1 over k minus 1 over k plus 1. Okay? So what does it mean? It means that if I want to calculate the first term, so Sn can be written in this form. Instead of this expression, where k is equal to 1 here, if you compare it with this one, this becomes 1 over 1 minus 1 over 2, yes? So what I have done, instead of this expression, using this formula, I have written this expression. You will see why this is important. It becomes like a telescope. Actually, terms actually start canceling each other one by one. For the next one, instead of this expression, I would write 1 over 2 minus 1 over 3. Yes, hopefully understandable. Instead of this expression, I choose k equals to 2. So this becomes equal to 1 over 2, 1 over 2 plus 1, which is 1 over 3. And exactly for the same reason, the next one becomes 1 over 3 minus 1 over 4. And then if I continue, the very last one becomes 1 over n minus 1 over n plus 1. But now, if you'll see, this sum, which is called the telescopic sum, the reason is that when I add them, this term cancel this term cancel the next term, this term will cancel the next term, this term will be cancelled with the previous one. And what is left for me is just this one and the very last one. Yes, so it means that I was able for this particular case to find a closed formula for Sn. Okay, so this new sequence is actually discovered now. So I take the limit of this Sn when n goes to infinity. So this becomes 1 minus 0 becomes 1. The reason is that the limit of this part is 0. Because this limit of this sequence is 1, we would say that the given series converges to 1. And this is just, I'm just giving you a flavor that how can these things work. Sometimes it is very hard to discover this pattern of a telescopic sum, and as I told you, most of the time the problem is that we cannot find a simple formula for the sum of the first n terms. This is why we have to invoke other theorems to realize if our series, the given series, is actually convergent or not. Okay, any questions so far? Okay, there is a famous series, is called harmonic series, and even though it seems to converge because it grows very, very slowly. I don't know if I remember correctly, you need to go above 100 million or something terms so that this sum becomes greater than 20 or something like that. I'm not completely sure about that, but I mean, the speed of increasing it is very, very slow, but finally you should be able to show that this diverges to infinity. So this sum, even though grows very, very slowly, but eventually it becomes greater than any pre-assigned positive number. Okay, so this is a very famous series, so you need to know its name, and then you need to know that this is an infinite series. That is a divergent series, and it is called harmonic series. So we want to show that the harmonic series diverges to infinity. I intentionally want you to see this proof because the idea of the proof going on here is actually used in a lot of exercises in the future. So I will talk about them again later. So here you need to consider this function f of x equals to 1 over x. So if I want to have a rough sketch of the graph of this function, I only consider that branch where x is positive, yes, because you know that this function has two branches, one here, one there, but this is for negative numbers and n cannot be negative, so we just consider the other one. I'm not drawing the graph to a scale. I just want to see, I want to tell you what the idea is. So for example, assume that this is 1. So you see that when I put 1 here, f of x should be 1. Let us consider this is 1, and the scale on the x-axis and the y-axis are quite different. But let us don't worry about that. Let me take this one to be 1. Okay, so this is 1. If I go up here, because this function is y equals to 1 over x, or let me write it as f of x 1 over x. So if I ask you what is this height, you would say the height is f of 1, yes? Let me write it generally here. So that is f of 1, but f of 1 is equal to 1, yes? So I can just clean that and write 1. Yeah, sometimes working with these things are hard. So this becomes 1. And let me go to the next step. This is 2. Then if I go up, if I ask you what is the length here, you would say this is the function 1 over x, and this x is 2, so the height that I face here is 1 over 2. The next one, if I ask you the same thing, and if I go up, and if I ask you what is this height, you would say it is 1 over 3. Okay? But now what we want to do, I want to continue this. I want to complete the rectangles here. So I will construct a rectangle here. And now if I ask you what is the area of this rectangle, it is very simple to calculate, yes? Because the width is 1 unit and the height here is also 1 unit. So if I ask you what is the first area, so the first area becomes 1. If I ask you what is the area of the second rectangle, what is the second rectangle? You complete the rectangle here. And if I ask you what is the area of this second rectangle, you would say that again the width is from 2 to 3, which is 1 unit, but the height here is 1 over 2. So if I ask you what the area is, you multiply this by that, it becomes 1 over 2, and you add it here. Okay, and then let me just do once more here. So if I go to 4, and then I complete this rectangle here, and this is now 4. And if I ask you what is the area of this rectangle, you immediately tell me that the height is 1/3 and the width is 1, so it becomes 1/3. So it becomes clear that when I am adding the areas of these rectangles, I am actually generating this series. Yes. And if, for example, I continue this method until, for example, number n, assume that here is n, and then of course let me be a little bit more careful here. So this will continue, actually it becomes closer, and then so let us assume that this is n plus 1 and this is n. Okay, so you have continued here until you reach to number n, and then you continue one more step, you reach to n plus 1, and then you complete the rectangle here. And if I ask you what is the area of this rectangle, the width is again 1 unit, but the height is this one. What is this height? It is 1 over n. So if I continue, it becomes 1 over n. Now if I ask you what can you say about this, you would say this is the sum of all these rectangles, the areas of all these rectangles. And you see that I have extra parts when I am actually calculating. So the area of the sum of the area of these rectangles is larger than the area below this curve. But if I ask you, so it means that this is greater than the integral from 1 to n of f of x dx. Yes? Because if I ask you what this is, you would say that this is the area below this curve from 1 up to let me write up to n plus 1 here, sorry. So the area, this area that I am right now showing for you, is the area below this curve from vertical line x equals to 1 to vertical line x equals to n plus 1, which you really know that this is given by this integral. But calculating this integral is simple. This becomes integral from 1 to n plus 1, 1 over x dx. But this integral is ln of x, ln of absolute value of x from n 1 to n plus 1. So this becomes ln of n plus 1 minus ln of 1. But ln of 1 is 0, so this becomes this. So we were able to show that Sn, what is Sn? Sn is the sum of the first n terms in this series is greater than ln of n plus 1. But we know that the limit of ln of n plus 1, when n goes to infinity, it becomes infinity. So this means that the limit of s of n is also infinity, because s of n is greater than this sequence. When this is infinity, it means that the harmonic series diverges to infinity. Okay, so this kind of reasoning, it's actually appeared a lot in the exam, so you need to understand it quite well. Is that understandable here? Or, yeah, good. Okay, another very important and common series is geometric series, and this is very good because whenever this appears, then everything is very simple. You need to realize what a geometric series is, and then fortunately there is a very nice and simple theorem that tells you that when this series converges and when it diverges. Okay, what is the main characteristic of geometric series is that you have the sum of some terms, but each term is obtained from the previous term by multiplying the previous term by the constant number r, which is called the common ratio. Okay, so you see here I start with an arbitrary number. Each time I multiplied it by r, it becomes ar, and if I multiply this by another r, it becomes ar squared. If I multiply it by another r, it becomes ar cubed, and this is the form of my series. This is called the first term for the natural reason, and this r that I am multiplying all the time is called the common ratio. So whenever your series looks like this, it's called a geometric series. Okay? And there is an important theorem which is not hard to prove at all, but let us just mention that. Of course, there are very special cases, but they are not important. Of course, it is clear when a is equal to 0, all the terms are 0, so it means that it converges to 0. But the important parts are actually this part, which is very important. If the common ratio lies strictly between -1 and 1, then this geometric series converges. And the fortunate thing is that we also know the sum. The sum is the first term divided by 1 minus the common ratio. And of course, if this does not happen, and this special case does not happen, then the series diverges. And then you can see that if r is greater than 1, the series diverges to infinity. If r is greater than 1 but a is negative, it diverges to negative infinity. And if r is just smaller than minus 1, and a is not 0, of course, it simply diverges because the terms become alternatingly positive and negative. So it neither goes to positive infinity nor goes to negative infinity, it simply diverges. Okay, so if you recognize that the given series is a geometric series, then your task is very simple actually. You don't need to do these things. For example, determine if the following series are convergent. If they are, determine their sum. So for example, let us concentrate here. Usually it's not hard to recognize this, so I would prefer myself to write some terms of the few first terms of this series. So it becomes minus 5 to power 2 and 8 to power 2 times 2, which is 4, yes? Because you see that the series starts from 2. And then the next term plus, I put 3, it becomes minus 5 to the power of 3, 8 to the power of 6. Let me do once more. If I put 3, it becomes, if I put 4, it becomes minus 5 to the power of 4, and this one 8 to the power of 4. And then it continues. But do you see that this is a geometric pattern, yes? Do you see that? Because every term is obtained from the previous term by multiplying a minus 5 in the numerator and 8 to power 2 in the denominator. Yes? I am multiplying the denominator by 8 to power 2, and I'm multiplying the numerator on each step by minus 5. So this means that this is playing the role of the common ratio. So indeed, this is a geometric series. So geometric series, if I ask you what is A is the first term, which becomes, I don't know, 25 minus 5 to power 2, 8 to power 4, which is 2 to power 12. So it is actually, I don't know, 2048. So this is A. Yes? 8 to power 4, 2 to power 12. No, even bigger than that, 4096. So I don't know, you can calculate this yourself. So it becomes 4096. Yes, and if I ask you what is the common ratio is minus 564. So it means that the series converges. Why? Because the absolute value of r is smaller than 1. R is somewhere between minus 1 and 1. According to this problem, if r is between minus 1 and 1, the series converges. Okay, and then it converges to A, which is 25 divided by this number, and then divided by 1 minus 5 over 64. And then you calculate this number, and that would be the sum of your series. So for example, if I want to do this one quickly, if I put 0, I get the first term 2 to power 0, e to power minus 3. The second term would be n equals to 1, 2 to the power of 4, e to the power of minus 2. If I put the other term, it becomes a 2 to the power of 5, e to the power of minus 1. And I hope that you can convince yourself that this continues. So it means that we can immediately understand what r is. R is 2 divided by e. Yes? Every time I am multiplying the numerator by 2 and the denominator by e. And the first, and of course the absolute value of r is less than 1 because e is more 2.7 something, so this is smaller than 1. So the series converges, and a of course is 8 e to the power of 3. Yes, this is 8, and I bring it up, it becomes 8 to the power of 3. So the series converges to 8 e to the power of 3, 1 minus 2 over e, so 8 4 e minus 2. Okay, so something like that. So if you can recognize that your series is a geometric series, your task is actually very simple. Okay. There is an extremely important and simple fact here. Okay, it's very important and simple fact. And you see that I have written an nth term test for divergence of a series. So this test is not capable of giving you if the series converges or not. But it might reveal that the series diverges. How? If this series converges, there is a theorem that guarantees that if you take this nth term and just take the limit of the nth term, it should be 0. So it says that if it convergence gives rise to the limit of an to be 0. But not the other way around. If the limit an is equal to 0, there is no guarantee that the series converges. Okay? But if the limit of an happens not to be equal to 0, you can conclude that the series diverges. So you see, this is technical, so you need to understand it very well. For example, to understand why the other way around is not correct, do you remember if I ask you about this series? This was famous. This is harmonic series, and we realized harmonic series diverges to infinity. But if I ask you what is the limit of this part when n goes to infinity, it becomes 0. So you see that if the limit becomes 0, there is no guarantee that the series converges. But if the limit happens not to be equal to 0, you can immediately conclude that the series diverges. Okay? So this is the content of this remark. For example, this is the module question. Investigate whether or not the following series are convergent. So you see, this will work here. For example, number 1. First of all, this is very important. If you want to see a series converges or diverges, this is the first thing that you need to check. You take the limit of an. If it happens to be 0, you don't know what is happening. It might be convergent or it might be divergent. So you need to use other tricks and techniques to be able to understand if it is convergent or divergent. But if you are lucky and the limit happens to be a number which is not equal to 0, that's the end of the problem. You just conclude that the series converges. The series diverges. If this number that you get for the limit is positive, you can say that you can say more actually. You can say this sigma, the sum goes to infinity, and if L is negative, you can say that the sum diverges to minus infinity. But if L becomes 0, you need to do it in a different way. Okay? So here, for example, if I want to check if it is convergent or not, so I just calculate the limit of this part when n goes to infinity. So this becomes cosine of pi over infinity, which is 0. But cosine of 0 is fortunately 1, and 1 is greater than 0. So I conclude that the series diverges to plus infinity. So number 2, the same story. Okay, so the first thing that comes to mind is just checking this. So because this is so simple, remember that whenever you want to see what is the situation of a series, check this one. It is very easy to check. Okay, so what is happening? It becomes arctangent of infinity. Of arctangent of infinity, the limit of arctangent of n when n goes to infinity is actually pi over 2, if you remember my lesson on these kinds of functions. So it becomes pi over 2, and then it becomes 2 over pi, and this is again positive. So it means that the series diverges to infinity again. Okay. There is also one important theorem here it is important, it tells you that it doesn't matter if you start from 1 or a bigger number. So this is if and only if. This IFF means if and only if. This means that if this series converges, this series also converges, and the other way around. So it means that if this series, for example, n starts from 2, an up to infinity, this converges. This is the same thing. N, if you start from 1, that also converges. And if this converges, this also converges. So then the few terms in a finite number of terms from the beginning of the series, if you eliminate them, it doesn't change the behavior of your series. Of course, it will definitely change the sum, but not convergence or divergence of the series. So if I ask you if this is S, if this is convergent to S, if I ask you what is this, you would say this is convergent to S minus the first term, of course, because the first term is being eliminated. But the behaviors are the same. Okay, so that's the content of this theorem. And of course, another very important theorem is that if you have two series, both of them converges. For example, one of them converges to number A, the other one converges to number B. If you take this series and multiply each one of these terms by a constant number C, you get a new series. This new series also converges, and it converges to C multiplied by the sum of this series. And if you have the sum or the difference of these two series, definitely it also converges. If it is positive, it converges to the sum of the sums, and if it is negative, it converges to the difference of the sums. And if each term of this series is smaller than or equal the corresponding term of this series, then definitely the sum of this series is also less than or equal to the sum of that series. So these are very easy things to prove, but let us forget about the proof. You need to know them. Okay, for example, let us consider this one. We want to determine the sum of the following series. Okay, by the way that I have written the question, it means that it is guaranteed that this series is convergent. It is asking you to find its sum. So how should we do that? For example, you can consider two series. One series is 3 over 3 to the power of n plus 2. N goes from 0 to infinity, which of course if I simplify that, it becomes this. And let me consider the other scenario. It is 2 to the power of n, 3 to the power of n plus 2. N goes from 0 to infinity. Okay, immediately it becomes clear. For example, this is a geometric series. Why? Because if I put 0, it becomes 1 over 3. If I put 1, it becomes 1 over 3 to the power of 2. The next one is 3 to the power of 3. And then you have this. And if I do the same thing here, it becomes 1 over 3 to the power 2, 2 to the power of 1, 3 to the power of 3, 2 to the power of 2, 3 to the power of 4, and etc. So here the A value is 1 over 3, the R value is 1 over 3, so it is less than, the absolute value is less than 1, so it's a geometric series and convergent. Here A is 1 over 9, and if I ask you what is R in this case, the numerator is always being multiplied by a 2, the denominator is always being multiplied by a 3, so this is 2/3, and again the absolute value is smaller than 1. So this is composed of two series, yes? Each one of these series are convergent, so it means that I calculate the sum of the first one. So let me give them names, A1 and R1, A1 and R2 here. S1 is 1 over 3, 1 minus 1 over 3. So it becomes 1 over 2. And S2 is 1 over 9, 1 over 2 over 3 is 1 over 3. So the full S is S1 plus S2, 1 over 2 plus 1 over 3 is 5 over 6. So sometimes this is also useful. So you see, I was able to realize that I can decompose this series into two series and hope both of them are convergent. Okay, but the main theorem that is actually very much used in the questions in the exam is the theorem which we call it the integral test. So it's important to understand this test. The function f has three conditions. It's important to understand these three conditions. So it is positive. What does it mean? It means that for all x, f of x is positive. This is the meaning of a function being positive. It is continuous, so it means that if you can draw the graph of the function with one pen stroke, there is no break in the graph. And it is non-increasing. It means that it might be flat or it goes down, okay? But it cannot go up. The graph of the function cannot go up. So this is these three conditions. Assume that your function is have these three properties on an interval like this, where n is a positive integer. So from a positive integer onward, the graph is always above the x-axis. It means it is positive. You can draw it with one pen stroke. It means it's continuous. And it is going down or remaining flat. It means non-increasing. The nice thing is that if you have this kind of a function and use the function to define a sequence, okay, then this series that is formed by this sequence and the improper integral here either both converge or both diverge to infinity. So why this is a useful test? Because if you remember, I spoke a lot about improper integrals, so you have a lot of knowledge how to understand if this integral is convergent or divergent. This relates the convergence and divergence of a series, which is a new concept, to what you already know in principle, how to understand it. So this is from this perspective is good, but it is extremely important. You can use this theorem for a function generating a sequence. The function should satisfy these three conditions. Okay. So for example here, this is also an analog of p integrals. Yes, p integrals. Do you remember? That's exactly what we want to use here. Integral of a number up to infinity, 1 over x to power p dx, which we covered last time. This is called the p integral, and we realized there that if p is greater than 1, this series converges, and if p is less than or equal to 1, sorry, not series, this integral converges, and if p is less than or equal to 1, this integral diverges. So now, for example, let p be a real number. The series this is called the p series. If I ask you what is one series, it means that you put p equal to 1, then you just get the harmonic series. Yes? So harmonic series is a special case of p series where p is equal to 1. Use the integral test to show that the p series converges if p is greater than 1 and diverges to infinity if p is less than or equal to 1. So here, what type of function I have? F of n is 1 over n to power p. Yes? So this means that the function that I am looking for, is actually here, is 1 over x to power p. And I am interested to see if this function, if this series is convergent or not here. But this function is, let us consider this function, and let us consider, for example, this interval from 1 to infinity. So here I am giving the role of n in that theorem to 1. Now, let us consider this interval. This is this interval. And let us consider this function. This function is always positive if I am on this interval. I am on this interval, x is greater than 1. So this is always positive. It is continuous because the only discontinuity, the only possible discontinuity happens at 0, but 0 is not included in this interval. And it is actually decreasing. It's non-increasing. Why? Because if I increase the value of x, the value of the function goes down. So this is an decreasing function. So this function on this interval enjoys these three properties. So it means that this series formed from this function and this integral from 1 to infinity of the function, they simultaneously converge or simultaneously diverge together. But we know about this before, based on previous lesson. If p is greater than 1, this converges. And if p is less than or equal to 1, it diverges to infinity. So I'm not writing all the details. I'm just speaking about them. But in the exam, you need to write them down. Okay? So you see what I have written here as this statement is correct. That is also a very important series to remember. So I would recommend you to memorize that this p series converges when p is greater than 1 and diverges to infinity if p is less than or equal to 1. Any questions? No questions? Yeah, please interrupt me. I sometimes forget to ask you, is there any questions or not? Okay. For example, show that the... Yes, do you have questions? No? Okay, show that the following series converges. Okay, for example, the first thing you need to do, so here, you don't need to use this. You see, 1 over 1 plus n squared, if I take the limit of this one, this becomes 0. But don't think that you can conclude that this is 0. Unfortunately, when it becomes 0, both situations are possible. So I cannot conclude anything here. But immediately, if you see, you can see that you can use this integral test very simply. So what is the function involved for this series? The function is you replace n with x, it becomes 1 over x squared. Now let us, for example, consider interval 1 to infinity. So you need to write them down. Be careful in the exam. If you want to use the integral test, you need to define your function. You need to say that I am checking these conditions are satisfied. So I would say f is positive. Yes, do you agree? So let me write it. If I want to write it more carefully, I would say on the interval, for example, 1 to infinity, f is positive, f is continuous, and f is decreasing. Yes. So you need to show that you are respecting the conditions. Therefore, instead of checking the divergence or convergence of this series, I can check the divergence and convergence of this improper integral. Yes? But you need to write these things in words in the exam. Okay, but this is a famous integral. This is arctangent. So in principle, if you want to write it in the exam, you need to write the limit integral from 1 to r, 1 over 1x squared dx, r goes to infinity, and this becomes arctangent of x. This is a famous primitive function from 1 to r. Then I have to take the limit, r goes to infinity. So this becomes arctangent of r minus arctangent of 1. But arctangent of 1 is pi over 4. Arctangent of infinity is pi over 2. It becomes pi over 2 minus pi over 4, which becomes pi over 4. Be careful. This number is not necessarily the sum of your series. Because this integral turns out to be a number, what you can say this improper integral is convergent, and according to the integral test, the corresponding series is also convergent. But in general, there is not a very nice relation between the sum of this series and the number that you get for the integral. Okay, that's it. So for example, let me just do this one also quickly. This is an exam question. So evaluate the improper integral. Okay, so when they say evaluate, so it means that this should be convergent. So how should I evaluate that? So number 1, I would write this integral, I would write it as the limit of r goes to infinity, integral from 1 to r, 3 divided by x squared plus 3x dx. So let me focus on calculating this integral. So if you remember this, you need to use partial fractions as we had before. So what you do, you write this as in the factorized form, and then you write a over x plus b over x plus 3, and then you have to multiply both sides by this expression and determine the values of a and b. So let me just do it quickly. So a becomes 1, b becomes minus 1. It's easy to guess here. Okay, and then when you do that, the integral from the integral of this expression, it becomes integral of the first part minus the integral of the second part, yes? But if I calculate the first one, it is ln of absolute value of x minus ln of absolute value of x plus 3, so I can combine them and write them in one ln, yes? Now I need to calculate it from 1 to r and then take the limit. Okay, so if I do that, the question mark becomes the limit of ln of absolute value of x over x plus 3 from 1 to r. R goes to infinity, yes? So this becomes the limit ln of r over r plus 3 minus ln of 1 over 4. And r goes to infinity. Okay, so what happens is that when r goes to infinity, the limit of this part becomes 1. Why? Because r over r plus 3 you can divide by r, and when r goes to infinity this is 0, so this becomes 1. But ln of 1 is 0, so the answer would be 0 minus ln of 1 over 4, but minus ln of 1 over 4 can be written as ln of 4. So they say evaluate the improper integral. You would say that the integral converges to ln of 4. So this is the value. And of course, this, you see, this is exactly the same function. So immediately you would say this is convergent, but the reason they have asked two questions because they want you to check the validity of the integral test here. So you would say for number 2, this is important. So you need to introduce your function. Your function is this one. And then, for example, you can introduce this interval, and you should say that f is positive, continuous. Why it's continuous? Because there are only 2 points problematic here. One of them is 0, one of them is minus 3. Both of them are being excluded from this interval, so it's positive, continuous, and decreasing. Why it is decreasing, it's clear, because when I start, by the way, I have to write 3 in the numerator because this is true. Okay, and it is clear, when I increase the value of x, the value of the function goes down, so this means that the function is decreasing, and then you would say that, okay, I can use the integral test. So you need to motivate why I can use the integral test, and then you can write the sentences yourself. Any questions? Okay, so if you don't mind, let us have a break for 10 minutes and then we come back and continue. Thank you. Okay, now let us solve another exam problem. So this is a recent problem. We want to show that this sum is less than or equal to ln of 2, and on the other hand, ln of 2 itself is less than or equal to this sum. So the idea of those rectangles are actually very useful, so it has been used a lot in the exam questions. So for example, let me describe it in patience here. So let me expand the sigma on the left hand side to have a better understanding of this. So k starts from n plus 1. It is mentioned that m and n are just positive integers. So this inequality holds for any choice of m and n as positive integers according to the claim of the problem. And you are supposed to show that. So let me just concentrate on the left hand side for the moment. So if I expand this sigma, this is nothing except 1 over n plus 1, 1 over n plus 2, 1 over n plus 3, And then of course you continue until you reach to 1 over n plus n, and of course this is the reason that you see 2n above, because n plus n is just nothing except 2n. So this is the left hand side. Okay, so let me just draw a diagram for the function f of x equals to 1 over x. And this trick that you learn here is actually very useful for finding both an upper bound and a lower bound. So you see here, on the one hand you are going to tell that this is smaller than this one. On the other hand, you want to show that this is greater than this one. Okay, so you need an upper bound and a lower bound for ln of 2. Okay, but let us see how we can do that. Again, if I just sketch a graph without having it into scale, so the function, I only concentrate on one branch of my function f of x equals to 1 over x. And now what we want to do, we want for this part, you need to consider rectangles that entirely are below this curve, because we want to interpret this as the sum of the areas of a bunch of rectangles, and I want to compare it with an integral which gives you the area below the curve. So usually this number should be an integral, should be the area below the curve, and this should be interpreted as the sum of the area of the rectangles. We can consider two types of rectangles: the rectangles that always lie below the area, this curve. So it is clear that if I add the areas of these rectangles, it is always smaller than the area below the curve. And we can consider these type of rectangles that are actually protruding outside from this curve. And it is clear that if I add the areas of these rectangles, then the sum of the areas is larger than the area between the curves. So one interpretation gives you an upper bound, and this new interpretation gives you the upper bound, the other one gives you the lower bound. So you need to concentrate on two types of rectangles if you are interested in both a lower bound and an upper bound. Okay, so let us concentrate here. So here it is clear, for this lower bound I need to concentrate on the rectangles that lie entirely below the curve. But the numbers are also important. Okay, so here you see, if it might be you think that you need to start from n plus 1. For example, let us concentrate that, assume that here is n plus 1. Of course, the next number is n plus 2. The next number is n plus 3, and it continues until, for example, at some point you reach to n plus n, which is 2n. Yes? Now let us, if I draw this vertical line, okay, and then I draw this vertical line, and I draw this one, and I draw this one, you immediately can tell me what are the lengths here. Yes, if I ask you what is the length of this one, you put this number in your function, it becomes 1 over n plus 1. That is good, so I start from here. And if I ask you what is the length here, you put this number into this function, it becomes the second one. Okay, and then the good point is that the width of all these rectangles is just 1 unit. Okay, so there is no difference between the area from the size point of view and the length of this. Okay, but I want to keep the, if I do this, then I would be in trouble, because this would be a rectangle coming out from this. I want to stay below the curve, so it means that I have to complete the rectangles in this form. But then if I ask you what is the area of this rectangle, you would say this is 1 unit multiplied by this, which is 1 over n plus 2. So it starts from this part. Okay, so the trick to get rid of that is to start from n instead of n plus 1. Okay, I start from n, and if I go up, and if I ask you what is, let me change my color, what is this length? It is 1 over n. What is this length? It's 1 over n plus 1, n over n plus 2, 1 over n plus 3, and then 1 over 2n. but I will complete the rectangles here in this form because I want to be below the curve. Yes. So this goes, for example, to the previous one here. Yes, I complete these rectangles in this form. Now, if I ask you what is the area of the first rectangle, you will take this length, which is 1 over n plus 1, and multiply it by 1. So it gives you the first one. You see, so if I start from n plus 1, I will lose this rectangle. So it starts from this one, but I want it in its entirety. So I start with 1 unit less, and everything becomes clear now. If I ask you what is the area here, the area here is this. What is the area here? The area of this was this one. And then if you continue, if I ask you finally what is the area here, you would say that this is exactly this one. So this sum that you see here can be interpreted as the sum of the areas of these rectangles. All of them are below the curve, completely below the curve. So this means that this is definitely smaller than the area below the curve. Yes, I hope that you agree with me. If I consider the whole area below the curve, the sum of the areas of rectangles is smaller than the whole area. But what is the whole area? It goes from n to 2n. Yes, so this becomes smaller than integral from n to 2n of my function. Okay, let me just stop here. Is that understandable? Do you have any questions? This is easier to ask. Do you have any questions here? Is everything clear?
Everything is clear.
Okay, good. And thank you for response. So we go here. So this becomes ln of absolute value of x, because this is a famous and simple integral, goes from n to 2n. So this means that this becomes ln of 2n minus ln of n. But I can write this as ln of 2n divided by n, but this is nothing except ln of 2. So I am done. So I was able to show that this sum is smaller than this integral, and I calculated this integral. It gives rise to this value. So I was able to show that this is smaller than this value. So this gives rise to the first part of the problem. For the second part, so you need to change your point of view from the rectangles below the curve to the rectangles above the curve. But of course the numbers here are different, m up to 2m minus 1. So again, what I do, let me expand that sigma. So sigma 1 over k goes from m to 2m minus 1. So this becomes 1 over m, the next one is 1 over m plus 1, the next one is 1 over m plus 2, and I continue until I reach to the very last one, which is 2m minus 1. I'm going one by one. So if you want to understand where this is coming from, this is nothing except m plus m minus 1. You see, because m is fixed, and then the first value is 0, the second value is 1, the third value is 2, and the mth value is m minus 1. So 2m minus 1 is actually can be interpreted in this way. Okay, but now you know that you want to make this sum greater than this, but you already know what is this one, so that's the integral, and that's the area below the curve. So you can just draw another, so you don't need that picture. So let me do another one here. So what we do, we have this function again. Yeah, this should be a copy of that function, but it's hard to draw it precisely. But a starting point, where should be starting point? But this time, remember, I want to concentrate on these type of rectangles which protrude outside this region. So I would say that this is a good starting point. If I start from here, m, let us consider the next one m plus 1, next one m plus 2, yes, next one m plus 3, and it continues. So for example, it should continue until I reach to m2m minus 1. And then I go one unit further. So you see, the trick is something like this. If you are interested in the lower integrals, you add one rectangle from the left, but if you want to find the other part, you add one rectangle from the right. You will see why. Because now, if I ask you what is this length, hopefully you agree with me, this length is 1 over m. This length is 1 over m plus 1. This length is 1 over m plus 2. And this length here is 1 over, let me write it here, 1 over 2m minus 1. But now let me complete the rectangles. I want to complete the rectangles here, and then here, and then here, and then finally for the last one here, sorry. Yes, so these rectangles. And now I am asking you the same question. If I ask you what is the area of the first rectangle, the width is exactly 1, and then you multiply it by the height, which gives you exactly this. And if I ask you what is the area of the second rectangle, you multiply the width, which is again 1, by the height of this rectangle, which gives you this. And let us check the very last one to make sure that we have done it correctly. If I ask you what's the area of the last one, you multiply the width, which is exactly 1, but you multiply it by this height, which is 2m minus 1, 1 over 2m minus 1. So you see, this can be interpreted as the area of these type of rectangles. Okay, and it's completely clear. So can you tell me what should I write here? It is greater than what? Can you tell me? Yes? I want to compare the sum of the areas. Yes?
From 2m, from 2m to, no, from m to 2m.
Yes, yes, from m to 2m. And you see that it is very, very important. If you don't have this 2m, you will be in trouble. I hope that you understand. You have to add 2m if you want to have an upper bound. And you have, let me tell you as a rule of thumb. If you want to find an upper bound, you need to add one more line here after this. And if you want a lower bound, you need to add one line before the minimum. So this is a rule of thumb that you can keep in mind. It helps you. Okay, and then as you said, that's exactly true. So this is greater than equal to the integral from m to 2m f of x dx. Okay, f of x is just 1 over x. And then the same scenario, this is exactly the same integral, you see. This integral you see here is exactly the same integral. The only difference is that instead of letter n, I have letter m. So it means that I can calculate it. It becomes ln of 2m minus ln of m. And then this becomes exactly ln of 2 again. Yes, so yes, that's correct. So it means that this sum is greater than ln of 2. So this is a very nice and important trick that they have used several times, I think, in the exam, different exams. If you have any questions, we go to the next problem. Any questions here? Okay, good. Okay, so this is also an exam question. Might be this is a little bit harder. Let us see. 2017 show that the inequality holds for all n greater than or equal to 1, and they have also given you a hint. The sum is an upper bound for an integral. By the way, let me go back and tell you something. Of course, in these functions, I am dealing with 1 over x. But there is not a big difference between this function, for example, with this function. Why? Because what is important for us is the continuity, which is this one is also continuous, and positiveness, this is also positive, and being decreasing, this is also decreasing. Of course, the graph is not exactly like this graph, but it has the essence of this graph. So this kind of arguments is always valid if the function involved has these three properties. One of the simplest, probably the simplest function with these properties is 1 over x, and there are many questions regarding 1 over x. But this behavior can be found for any functions having those three properties. So for example, here in this exam question, what I see, if I consider this function, the function is more complicated, I agree, but this I hope that you agree with me that this function has the same three properties. Of course, on an interval, for example, from 1 to infinity, you don't need to, because you want to calculate for n greater than or equal to 1, you can limit yourself to this interval. On this interval, hopefully you agree with me, it's continuous because the only problems are at 0 and 0 is excluded, so it is continuous, it is positive, and it is decreasing. Why? Because when I increase the value of x, the numerator is constant, the denominator is going higher, so it means that overall the function goes down, so the function is decreasing. So this function has those three properties. Yes? Positive, continuous, decreasing. Okay, so how can we solve this problem? So what can we do? Because we want to find that sum is an upper bound for an integral. Okay, so might be the idea is a little bit different here. Okay. First of all, let me concentrate on this integral. Integral from, let me write from 1 to infinity. Okay, and then let me write dx over square root of x plus 1, d of x. Yes. Okay, so let me teach you the same thing. So what I want you to understand here, so let me just draw something, have a picture here. I don't know, hopefully it will work. But what is important for you is just the graph that I am drawing has those three properties. Yes, it is positive, it is continuous, it's decreasing. Okay, so this function is f of x equals to 1 over square root of x plus 1. Okay, and then if I ask, if you see this sum can be interpreted in the same way. So, for example, if I ask you, let me start from 1, and then if I ask you what is this height, you would say this height is when I replace x with 1, which gives me the first term of this sum. Yes? And then I go to the next one, number 2. And if I ask you what is this one, you will give me what is the height here. The height here is when I replace x with 2, which gives me the second term in this sigma. And then by that rule of thumb, you know that I need to go 1 unit more. This is up to n, so I need to continue this process. Yeah, hopefully this will work. And then I reach at some point to n, and let me go to n plus 1 again. Okay, and then let me complete the rectangles. You see, it is important that this behavior is also here. Yes, so now if I ask you what is the area of this rectangle, you can answer that. Yes, what is the area of this rectangle? It is f of, let me write, instead of f of x, let me just simply write f of 1. This is f of 1. And then if I ask you what is the area of this rectangle, it is just f of 2. And then if I continue, what is the area of this rectangle? This is f of n. These are the areas. And then if I add them, the sum of these areas becomes this sigma here. So sigma k goes from 1 to n, 1 over square root of k plus 1 is nothing except f of 1 plus f of 2 up to f of n. And then these are the areas. Okay, this is definitely greater than the integral from 1 to n plus 1. My function dx. Yeah, let me just stop here. Is everything understandable so far? You see, I am using the same rule of thumb. I want to find a lower bound for this sum, so I need to consider these kinds of rectangles. But I told you, as a rule of thumb, if you want to consider the upper bound, you need to go 1 unit more to the right. So okay, because then in that case, when I add them, it becomes this sigma. Is that understandable so far? Okay. Yes. If you have any questions, please. But the problem is a little bit harder because you need to talk a little bit about this integral. In the previous problem, this integral was very easy to calculate. Okay, this problem is harder. The rule is exactly as before, but this integral becomes harder. This is why in the beginning I was thinking that can we continue in this way. Now I realize yes, we can. Can you tell me how should I calculate this integral? It seems a little bit hard, but that was a little bit, I was looking ahead of me. I was thinking that might be we will not be able to calculate, but we can calculate this integral. That's the method of substitution. Can you tell me what can I call u so that I can solve this problem? I would say let u be equals to square root of x plus 1. Okay, if I tell you this, I expect you to be able to solve the rest of the problem because the rest of it is coming algorithmically. What is the next step? You need to calculate du, but what is du? The derivative of the square root is just this one multiplied by dx, and that is exactly, now you see what's happening. Dx divided by square root of x appears here. Okay, so this means that 1 over square root of x dx is 2 times du. But x goes from 1 to n plus 1. This then implies that u goes from 2 to square root of n plus 1, yes? Because if x is 1, I put 1 here, u becomes 2. And if x is n plus 1, I put n plus 1 here, this is the upper bound. So this integral, if you don't mind, let me call this integral I here. So therefore I becomes equal to integral from 2 to 1 plus square root of n plus 1. Instead of dx over square root of x, I put the 2 du. And instead of the denominator here, I just simply put u. But this is also now a famous integral, yes? This becomes 2 ln of absolute value of u. It goes from 2 to 1 over 1 plus n plus 1. This means that I put that number, because it is positive, I don't need absolute value, minus 2 ln of 2. But what can I do here? I can write it as ln of 1 plus square root of n plus 1 to power 2 divided by 4. Yes, is that understandable? Because you know that I can put this on top of this, I can put this on top of this, 2 to the power 4 becomes 4, 2 to the power 2 becomes 4, and then because I have the difference between two ln's, I can write one ln and then divide them. ln of x minus ln of y is equal to ln of x over y. Okay, I think more or less we are done. And usually they don't give you the exact form. And this is now simple. So let me continue this. This becomes ln. If you don't mind, let me square it. The first one to the 2, 2 times the first one times the second one to the 2, and then divided by 4. And if I simplify this a little bit, so this becomes ln of n plus 2 plus 2 square root of n plus 1 divided by 4. So let us see what we have done so far. So we were able to interpret this sigma as the sum of the areas of these rectangles, and then it is clear that this sum is greater than the area below the curve, which is this integral, and then up to here I just calculated this integral. So it means that this sigma is greater than this value, and I hope that you agree with me. This value itself is also greater than ln of n over 4, yes? Because this expression is greater than n, because I am adding positive numbers to n, so the numerator is greater than this numerator, the denominator is the same, so the whole fraction is greater than this fraction, and because ln is an increasing function, ln of this bigger number is greater than the ln of this smaller number, and then we are done. Yeah, that might be a little bit harder problem. But you see, I myself was confused in the beginning because I was not sure that we were able to calculate this integral, but you see that I used exactly the same rule that I just told you it's good to know as a rule of thumb. Any questions? Okay. So this is also another type. So let me. There are many problems of this type in the exam, but yeah, there is actually. This is the end of the lesson, more or less. So yeah, let me solve this one as well, because we have one more session. I wanted to keep that session for solving if possible. I don't know what is your suggestion. Do you think that would be a good idea if on Monday I just pick an exam that I haven't solved any questions in my lectures and go from the beginning to the end? Do you think that this is useful?
Yeah.
Okay, so hopefully if everyone agrees, because most of the people actually doesn't join the lectures, but if you think I want to keep that Monday, just pick one of the exams, because you see that I have solved a lot of exam questions, but I will choose one exam that I haven't solved any one of those questions, and then I go from the beginning to the end. Hopefully we can finalize it in 2 hours, and then that would be a good recap, I would say, for this one. So yeah, if you don't mind, let us keep this last session for teaching. If there is some minor things left, I will upload this PDF file, and then you can go through it yourself. And of course, if you have questions, you can let me know about that next time. Okay, so let me just solve this problem. That's also a little bit a recent exam. Show that you see, the reason that I'm interested in this solving this problem for you, because this is the first time they are asking you to find this limit including a sum. So this is why I want you to see how to solve. If you remember, we had these kinds of limits before, but that limit was different. Do you remember? That was an important part of the lesson. If I can write my limit containing a sigma in this very particular form, which I don't think we can do it here, can we? You see here the factor is 1 over ln of n, but the factor I need here is 1 over n. If I can write it like this, then you remember hopefully from the previous lectures, instead of calculating the limit, you calculate the integral of the function. Okay, so this is the trick of solving these kinds of limits. But this is the first time I see that this is not that type of limit, but probably we should be able to solve it with these kinds of arguments. And whenever this happens, usually you need a squeezing theorem. And a squeezing theorem I covered in the previous session for sequences. If I have a sequence I don't know, Bn between Cn and An. If the limit of this is L, the limit of this one is L, so you can conclude the limit of the middle one is also L. So whenever you want to calculate the limit of a sequence and there is nothing standard going on there, so this is the way that you have to do it. Okay, so I think by the experience that you have got so far, the first one should be easy, yes? Because this is the same sum. You want to show that this sum is greater than the number. Okay, so this is exactly the same thing, so let me just do it quickly. Okay, so if I draw the function 1 over x here, something like this, so we want to make this bigger. So do you remember I need these external rectangles. For external rectangles I need to go one more to the right. So if it ends at n, I need to go up to n plus 1. That was the trick, yes? So here I will take this one is 1, the next one is, for example, 2, the next one is 3, and then the last one I do not stop at n, I stop at n plus 1. Of course the previous one is at n, and then I complete these squares, so now you know what to do immediately. Yes, so I need to add these areas. If I ask you what is the area here, what is the area, you need to multiply this length by 1. This length is f of 1, which, so sorry, this, I don't know why I wrote x, this is f of x, 1 over x. So this becomes 1 over 1. The area here, what is the area here? It is 1 over 2. The area of the next one is 1 over 3, and finally the area of the last one is 1 over n, and I am adding them. So this sum that you see here is the sum of these areas, and of course this sum is greater than the area below the curve, yes? And the area below the curve is integral from 1 up to n plus 1, 1 over x dx. Okay, so this means this is equal to the ln of absolute value of x from 1 to n plus 1, which becomes ln of n plus 1. So I was able to show that this is greater than ln of n plus 1. Automatically, it's also greater than ln of n. So I was able to show that this sum is greater than ln of n. Okay, but because of what I told you, if you want to calculate this, you need to remind yourself of a squeezing theorem, and in a squeezing theorem we not only need an upper bound, we also need a lower bound. So even though they haven't mentioned to find a lower bound, you need to understand it yourself because you want to use the squeezing theorem. So what can I do? So if you don't mind, let me write it compactly. So what we learned so far, the sigma of 1 over k goes from 1 to n, is greater than ln of n. So let me divide both sides by n. The motivation is coming from this division. Sigma 1 over k goes from 1 to n, is greater than 1. So let us write it in this form. So 1 is smaller than ln of n, sigma 1 over k goes from 1 to n. This is something, oh sorry, this is 1 over. Okay, so let us keep this for the future. Okay, then I think this is now more or less very clear for you now. So if you want to find the other bound, what you need to do, you just go here and draw another graph for yourself, and then this time you want to concentrate on the other type of rectangle. So yes, so for the other type of rectangles, so what can we do here? Okay, so the trick, do you remember I told you that you need to go 1 unit to the left, but then it would be problematic here, yes? Because if I go 1 unit to the left, then it starts from 0, but 1 over 0 is not defined. So let us see how we can do that. This is a little bit different. So still I have to start with 1, okay? So do you understand what's going on? If I want to use the same trick, I need to go 1 unit to the left, it becomes 0, but 1 over 0 is not defined, so I cannot do that. Okay, and then I go to the other one, so let me make it a little bit bigger here. So this is this one, and the next one is 3. and then if I go up to, but this time I want to concentrate on these rectangles. Yes. So final one is n, and the previous one is n minus 1, but again I want to concentrate on these rectangles. Okay, so now if I ask you what is the area here, the area here is this length times this, but this one is 1 over 2, not 1. So the area here is 1 over 2, the next area is 1 over 3, and then if you continue, the last area is 1 over n. Yes? Okay, so that's what we can do. But it means that this sum, 1 over 2 plus 1 over 3 plus up to 1 over n, is smaller than the area below the curve from 1 up to n. 1 over x dx. So this becomes simply ln of n. Yes? Okay, now we add 1 unit manually by hand. We were not able to use the same trick there, but at least we can add 1 unit manually by hand. Okay, so let me add one more page here. Okay, so now hopefully you understand what I did. I wanted to use the same trick. I faced the problem here because it stands on 0, and unfortunately I cannot do that. But on the other hand, still I want to find an upper bound, so I need these type of triangles. So I started from 1 and I got this formula. But I want to have it from 1 up to this. Okay, what can I do? I just manually add 1 unit to both sides of this inequality. And then what happens here? The left hand side becomes sigma of 1 over k. Again, k goes from 1 to n as I want, but this time it is smaller than 1 over ln of 1 plus ln of n. So yeah, let me just take this with me to the other page. So here we were able to find that, but again motivation is the same. I divide both sides by ln of n with the same motivation because I want to have the same combination again. Yes, I divided both sides by ln of n. Okay, now if you let me go back here and bring this one with me as well. Okay, so yeah, I need to complete this myself. Here it was 1, if you remember. Here's also 1. Okay, now you see that I was able to squeeze this between 1 and this. So finally, comparing these two, I've got this 1 over ln of n, sigma 1 over k, k goes from 1 to n, on the one hand is greater than 1, on the other hand it is smaller than this. Yes? Now if I ask you what is the limit of 1 when n goes to infinity, this is a constant sequence, so the limit is 1. If I ask you what is the limit of the right hand side when n goes to infinity, this is again 1, because ln of infinity is infinity, 1 over infinity is 0, so the limit is 1. So the limit of the left hand side is 1, the limit of the right hand side is 1. So squeezing theorem gives me that the limit that I was looking for is also equal to 1. I'm trying to make these methods a little bit reasonable, you see, because otherwise it is so random that how should we know to do these things. But you see, I am using the same type of thinking all the time, and then if some new problem emerges, I will try to think a little bit and fix the problem. So for example, the difference between this one and the previous one was this is not exactly according to the rule of thumb that I just mentioned, because if I go 1 unit to the left, then I will face a problem. And then what can I do? Okay, I just momentarily forget about this technique and I find this, and then I realize I need a series from 1 up to this one, so it is clear I can add 1, and I was lucky it was possible to solve the problem. Sometimes if the problem is harder, even if you use these tricks, this doesn't work. But anyway, this worked here, fortunately. Any questions? Okay. So because there is no time, yeah, I would say that you can read this theorem yourself. Of course, it is also good to know how to derive that. Might be we can talk about this on this next session if you have problems. The reason that I mentioned this theorem from the book, because I saw that this example from the exam more or less uses the same idea in the proof of this theorem. So I recommend you go in the book and read this, the proof. I want you to understand how to get this. It's more or less the same idea of triangles, exactly the same thing. I don't think you will face any problems here. And then you can use this one to solve this problem and this problem. This is harder, and that's so if you want, probably we can spend some time on the next session to solve this one, but try to do it yourself first. This one of the exam and this one are using this theorem in the book. But the ideas are exactly these kinds of rectangles, inner rectangles and other rectangles. Okay, so let me just finalize what we want to say. There are 2 more important theorems. Well, of course, there are many details in these things, but I don't know how they can cover all these material. But anyway, these are the important ones that I want you to know. And this is a comparison test. It's very important. What does it mean? If I have 2 series, if I have 2 sequences satisfying this property, it means both my sequences are positive, and one of them is smaller than a multiple of the other one, where k is a constant. Ultimately is an expression when it comes to series. It means that after some terms, it might happen that this does not satisfy for the first few terms, but from some point onwards, this condition holds. Instead of saying so many terms, they just say ultimately. So ultimately means this. For some positive constant k. This is very interesting. Exactly as before, do you remember for improper integrals? If the bigger series converges, this would imply that the smallest series converges as well. If the smaller series diverges to infinity, it gives rise that the bigger one also diverges to infinity. So that is an extremely useful theorem to know. For example, this exam question, determine whether this series is divergent or convergent. Okay? So for example, the integral test will not work here. Why? Because this function is not a decreasing function. Yes, it's not easy to detect that, because when you increase n, the value of sign goes up and down, so might be it will affect you. Of course, you are also increasing the denominator. At least it is not easy to judge. On the other hand, if it is also easy to judge, might be it is not easy to talk about the integral here. So I'm not saying that might be you can think and find a way using integral test, but I would say that this is a simpler test to do. Okay, so what we do here, I start from here, so 2 plus, by the way, always make your brain conditional. When you talk about divergent or convergent, the first thing that you need to check always is to take the limit when n goes to infinity. Because if you're lucky and it becomes non-zero, then you immediately say it's divergent. But unfortunately, the harder questions are not like that. You agree with me that if I send n to infinity, the limit is 0. Why? Because this is a bounded function, so the numerator cannot exceed more than 3. The denominator goes to infinity, so the limit is 0. So unfortunately I'm in limbo situation, so it is not enough. So what I do, I start from here and try to see if I can cook up an argument. So do you agree that if I write this is smaller than 3, yes? Yes? Why? Because I kept the denominator exactly the same, and then you know that sign of any number is definitely smaller than 1, so the numerator is definitely smaller than 3, so the whole fraction is smaller than this fraction. But again, I hope that you agree with me if I write this. Yes? Why is that? Because the denominator of this is definitely greater than the denominator. And when the denominator is greater, the whole fraction becomes smaller. But this can be written as 3 times 1 over n squared. You see, it's exactly the same thing. So let me call this one an, and let me call this one bn. And then let me call, this is the k. Now you see an is less than or equal to kbn. On the other hand, do you agree with me that this is always non-negative? Why? Because the denominator is non-negative, and the minimum value for sign in the worst possible case is -1, so it means the numerator is also positive. So you see that what is happening, 0 is less than an is less than 3 times bn. So this is satisfied. But what do I know about sigma of bn? Sigma of 1 over n squared is a 2 series, yes? Do you remember I talked about p series? So p here is 2. So it's a 2 series. But if p is greater than 1, the p series converges. Okay? P is equal to 2 greater than 1. So this converges. And when the bigger series converges, the smaller series also converges. So this implies that sigma 2 plus sine n converges as well. Any questions? Okay, so let us skip this one as well, and let me finalize this session by the last theorem that I want you to know. This is also a very, very handy tool. A limit comparison theorem. Yeah, so but memorizing it is a little bit hard, so it's not hard to convince yourself, of course, but let me just immediately tell you. So if you have the limit of this ratio of two sequences, an and bn are positive sequences, you calculate the limit. I have forgotten to write this. You calculate this limit and it becomes L. Of course, L is either a non-negative finite number or positive infinity. There are two possible scenarios going on for the limit of positive numbers. If I have a sequence consisting of positive numbers, there are two scenarios at most. Either the limit exists. If the limit exists, definitely it should be positive because all terms of the sequence are positive, or it diverges. If it diverges, it goes to infinity. Okay? So you calculate this limit and you find L. Two possible scenarios, yes? Either you get a positive number for L or you get positive infinity for L. Okay? Of course, it might happen that this is not this one nor this one. For example, if I ask you what is the limit of sine n when n goes to infinity, this is neither a number nor infinity. So it's nothing. It's not a number. The limit does not exist. But assume that we are considering only these two cases. If this case happened, this test is silent. Okay? If L is a number and the lower one converges, this would imply that the above one also converges. Yes? And if L is positive and the lower one diverges to infinity, the above one also diverges to infinity. Okay? So this is extremely useful if you have these kinds of scenarios going on. Because you see that in the previous example, all the signs are positive. But for example, assume that this one single sign here is negative. Then I will have problem. I cannot say that this is smaller than this one. I need to think more about it. But this theorem is very nice in this regard. So here, what I recommend you, this is the way that I do it myself. Which term in the numerator dominates? Again, let me check if n goes to infinity what happens. Hopefully you agree with me. When n goes to infinity, the degree of the numerator is 3/2, but the degree in the denominator is 3, so it dominates and it goes to 0. So that test is silent here. Okay, so what I do, I would say that this term in the numerator dominates, so I go to scratch paper, so this in the numerator will dominate for large values of n, and n3 in the denominator will dominate, and then if I simplify that, it becomes this. Okay, so I will consider this. I would say that let an be this, and bn be this sequence. Okay, so this is the way that I found this sequence. Okay, ultimately, you see, I should have also written here ultimately positive. So yeah, ultimately, if n value is big, then this will dominate 1, this also dominates this. So definitely this is positive, this is also positive ultimately. Now let me calculate the limit of an over bn, n goes to infinity. So let us see what happens. So this becomes the limit 2n square root of n minus 1 divided by n3 minus n plus 1, and then divided by 2 square root of n squared. N goes to infinity. So if I simplify this a little bit, so this becomes 2n3 square root of n minus n squared, and the denominator would be 2 square root of n multiplied by n3 minus n plus 1. N goes to infinity. So if I divide everything by what? By n to the power of so how should I calculate this limit now? Let me see. The denominator, the degrees should be the same, because the degree here is 3 plus 1/2. The degree here is also the same. So okay, I have to divide by this expression. Okay, I divide by that, so this becomes the limit 2 minus n squared divided by 2n cubed square root of n. And in the denominator, it becomes 1 over n cubed. Yes. 1 over n cubed, yes, multiplied by n cubed minus n plus 1. So let me simplify it one more step and then we are done. So this becomes 1 over 2n square root of, and these are simple algebra. I'm worried a little bit about you if you want to leave the session, so this is why I'm doing it quickly. N goes to infinity. And then this limit is 0, this limit is 0, this limit is 0, so it becomes 2. And now you see that if I am lucky, if L is smaller than infinity, which it is, and if the lower one converges, it means if this converges, I can conclude that this one also converges. But do I have a good reason that this converges? Yes. Why? Because Bn is 2n to the power of 1/2 divided by n squared. If I simplify that, it becomes n to the power of 3 over 2. And this is a p series. Yes? And p is 3 over 2, which is greater than 1. So because this is a p series with p greater than 1, this Bn converges. And because the limit of an over bn is a number less than infinity, yes, so it means that because the denominator converges, the numerator also converges. So we realize that this series also converges. Okay?